A vast curtain of cosmic dust is draped across the celestial sphere, concealing from us 20% of the entire observable universe. Behind this obscuring veil, an immense and unidentified structure is pulling our own galaxy through space at more than 1 million miles per hour. We are unable to see this object. No telescope has ever captured an image of it. And yet, its gravitational influence extends across hundreds of millions of light years, drawing us steadily toward a destination we cannot perceive. This region is known as the Zone of Avoidance, and researchers have only recently begun to understand what it conceals. When we stand on Earth and gaze at the night sky, it feels as though the whole of creation is on display. This perception, however, is not accurate. Nearly 20% of all that exists is kept from our sight, hidden by an observational barrier that astronomers have named the Zone of Avoidance. It is much like exploring a magnificent mansion, only to find that 1/5 of all its rooms are permanently inaccessible. One would naturally be consumed with curiosity about the secrets or treasures that might lie behind those locked doors. This zone encircles the sky in a wide, thick band that follows the celestial equator. As scientists first began to chart the arrangement of galaxies throughout space, they encountered a perplexing anomaly. In specific directions, the galaxies seemed to vanish entirely from their surveys. The sky appeared strangely vacant within a broad swath that cut through certain constellations. Astronomers in the 1800s initially labelled this area the Zone of Few Nebula. They operated under the mistaken belief that these regions of space were simply empty. The truth is that space is not vacant there at all. Rather, something is obstructing our line of sight. This barrier is a direct consequence of our location inside a galaxy. Instead of observing it from an external vantage point, our place within the Milky Way puts us right in the galactic plane, enveloped by hundreds of billions of stars, immense clouds of gas, and thick veils of interstellar dust. To see the distant galaxies that lie beyond our own, our view must first pass through all of this intervening material. For most lines of sight, this is not a significant problem. Looking toward the galactic north or south pole provides a relatively clear window into deep space and faraway galaxy clusters. But looking directly into the plane toward the galactic center presents an entirely different challenge. The field of view becomes overwhelmingly crowded. Dense clouds of dust effectively absorb the light from anything located behind them. Innumerable foreground stars also create confusion for our instruments. This makes it exceptionally difficult to differentiate between a nearby star within our galaxy and a distant galaxy composed of billions of its own stars. The light from those remote objects simply cannot complete the journey to us through the obstruction. For more than a century, this cosmic blind spot was a source of great frustration for astronomers. They were certain that galaxies had to exist within these hidden areas. The universe, on a large enough scale, should appear generally uniform, regardless of the direction one looks. Having 20% of the heavens permanently hidden meant that 1/5 of all cosmic knowledge was inaccessible. Researchers could create maps of the universe's large-scale structure, tracing the cosmic web of galaxy clusters and voids. Yet, their maps always contained huge, empty gaps wherever the Zone of Avoidance intersected their observations. This frustration only deepened when new evidence suggested something of great importance was concealed within the zone. Calculations based on the movements of galaxies pointed to the existence of enormous concentrations of mass hiding behind the dust. Our own Milky Way galaxy seemed to be in motion towards something we could not directly observe. The invisible barrier was not merely obscuring random sections of the cosmos, it was actively hiding some of the most massive and influential structures in our local universe. What scientists would later find would fundamentally alter our understanding of our place in the cosmos. Our solar system is situated approximately 30,000 light-years from the Milky Way's core, deeply embedded within the galactic disk. A spiral galaxy can be visualized as a vast, rotating structure with arms extending from a luminous central bulge. We are located within one of these spiral arms, surrounded by the galaxy's dense population of stars. This position affords us a breathtaking, edge-on perspective of our home galaxy. As we look along the galactic plane, the Milky Way manifests as a radiant band of light stretching across the night sky. But this beautiful spectacle comes at a significant observational cost. The galactic disk is filled with more than just stars. Expansive clouds of dust particles, each one smaller than a grain of sand, populate the space between the star systems. These tiny particles originate from material cast off by dying stars, the explosions of supernovae, and powerful stellar winds. Over the course of billions of years, this dust gathers into thick, obscuring clouds that can span hundreds or even thousands of light years. The way dust interacts with light is particularly problematic for astronomy. Instead of allowing photons to travel unimpeded, the dust particles absorb them or scatter them in different directions. This effect becomes more pronounced at shorter wavelengths of light. Blue and ultraviolet light are scattered and absorbed with the greatest efficiency. In contrast, red and infrared light are better able to penetrate the dust. This same principle explains why sunsets on Earth have a reddish hue. Our atmosphere scatters away the blue light, which allows the longer, red wavelengths to reach our eyes. In the interstellar medium, cosmic dust produces a similar outcome, but on a far more dramatic scale. Gazing through the galactic plane requires looking through successive layers of these light-blocking clouds. Light originating from distant galaxies must journey through thousands of light-years of this dust-filled space to reach our telescopes. The vast majority of it never arrives. The photons are either absorbed or scattered randomly, becoming lost within the cosmic haze. This issue is most severe near the galactic center. The central bulge of our galaxy holds an extraordinarily dense concentration of stars, gas, and dust. Attempting to see anything beyond this region with telescopes that rely on visible light is a near impossible task. The view is so cluttered and dimmed that even the most luminous galaxies become undetectable. Beyond simple obscuration, scientists must contend with another major hurdle: confusion. Pointing a telescope toward the Zone of Avoidance reveals a field of view crowded with countless stars from our own galaxy. A faint, distant galaxy might be present in the image, but distinguishing it from the thousands of foreground stars is an immense challenge. Early astronomical catalogues often misidentified stars as galaxies, or they missed galaxies altogether because they were camouflaged against the stellar backdrop. The combined effect of dust absorption and stellar crowding establishes what is essentially an impenetrable wall at visible wavelengths. For many decades, this limitation appeared to be absolute. Astronomers had to accept that some parts of the universe would likely remain hidden forever, their secrets kept behind our galaxy's own natural curtain. Some had estimated that between 10 to 20% of the extragalactic universe might never be adequately mapped. It was then that researchers began to realize that visible light was not the only means of observing the cosmos. Other wavelengths, they reasoned, might be able to pierce the veil where optical instruments had failed. The central question became which forms of light could penetrate the galactic screen. A significant shift in how scientists comprehended cosmic motion occurred during the 1970s. For many decades, astronomers had charted the velocities of galaxies by analyzing how their light shifted. Light from a galaxy receding from our vantage point is stretched into longer, redder wavelengths, while light from an approaching one is compressed into shorter, bluer wavelengths. This principle, known as the Doppler effect, provides an exceptionally precise method for gauging movement through space. The universe undergoes a uniform expansion in all directions, carrying galaxies apart from one another like points on an inflating balloon. Based on this, every galaxy should display a redshift directly proportional to its distance. Those nearby would recede slowly, while more distant ones would move away more rapidly. This relationship, which had been discovered decades prior, suggested a smooth and predictable cosmic expansion, yet measurements consistently revealed anomalies. Some galaxies were observed moving slightly faster or slower than expansion alone could account for. These deviations, which came to be known as peculiar velocities, pointed to the existence of gravitational influences beyond the simple outward flow. Immense structures could be exerting a pull on nearby galaxies, causing them to drift toward these concentrations of matter. As scientists mapped these peculiar velocities in the 1970s, they noticed something extraordinary. Our own local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, was not merely coasting along with the expansion of the universe. The entire cluster appeared to be moving in a specific direction at an incredible speed. This velocity was determined to be 600 kilometers per second, or approximately 1,300,000 miles per hour. An unseen force was pulling on us, but its nature and location remained a mystery. Researchers carefully traced the direction of this motion, and the results indicated a region of the sky in the constellation Centaurus, situated deep within the Zone of Avoidance. Whatever was responsible for this enormous gravitational pull was hidden from view behind the galactic plane. Scientists could measure its influence, but they could not directly observe the source. Subsequent observations began to reveal the true scale of the phenomenon. The local group was not moving in isolation. Hundreds of other nearby galaxies exhibited similar peculiar motions, all streaming in the same general direction. The Virgo cluster, a massive congregation of over 1,000 galaxies, located 50 million light-years away, was also being drawn toward this mysterious region. Even more remote galaxy clusters showed its influence. The gravitational force necessary to move such enormous masses across such vast distances defied any simple explanation. Calculations suggested the presence of a mass equivalent to tens of thousands of galaxies, all concentrated in the hidden area. Some estimates placed this mass at 10 quadrillion times that of our entire solar system. In 1986, the astronomer Alan Dressler gave this invisible gravitational monster a name, calling it the Great Attractor. The name was a perfect encapsulation of both its function and its enigmatic quality. It was an attractor, a concentration of mass pulling on everything around it through gravity. Yet, it remained great in both its immense size and its elusiveness, concealed behind the cosmic curtain where telescopes could not peer. The discovery presented a profound puzzle. One of the largest and most influential structures in our cosmic vicinity was completely invisible to observation. Scientists knew it existed because of its effects, not because they could see it. The Great Attractor became one of astronomy's most compelling enigmas. Understanding its nature would demand new technologies and creative solutions. But first, researchers needed to understand why we could not see it at all. Right now, as you are in this moment, you are racing through space at a speed that would be difficult to process if you were to pause and calculate it. The Earth spins on its axis at roughly 1,000 miles per hour. Our planet orbits our star at 67,000 miles per hour. Our entire solar system circles the galactic center at over 500,000 miles per hour. Each motion is layered on top of the one before, carrying you through the cosmos at velocities your mind can barely grasp. And there is one more layer to add to this motion. Our entire galaxy, along with thousands of others, is being dragged toward an unseen destination at 1,300,000 miles per hour. The Great Attractor pulls relentlessly, its gravity reaching across hundreds of millions of light-years to influence the trajectory of massive galaxy clusters. To comprehend the scale of this gravitational influence, consider what is being moved. The local group contains roughly 80 galaxies, including giants like the Milky Way and Andromeda. Its total mass exceeds 1 trillion times that of our star, and this entire structure drifts toward the Great Attractor like a leaf caught in a river's current. The Virgo cluster, by comparison, dwarfs the local group. This massive collection contains over 2,000 galaxies and spans roughly 15 million light-years across, with a total mass reaching quadrillions of stellar masses. Yet even this titan responds to the gravitational call, moving toward the same hidden region. Beyond Virgo, dozens of other galaxy groups and clusters show similar motion. Scientists mapping these peculiar velocities discovered a vast region of space spanning hundreds of millions of light-years, all flowing toward a common point. This pattern suggested something more complex than a single massive object. Multiple structures might be combining their gravitational pull, creating a region of enhanced density that attracts matter from all directions. Measurements of the cosmic microwave background radiation confirmed the motion. This faint radio glow, a remnant from the Big Bang, fills the entire universe. As we move through this background radiation, it creates a slight temperature difference between the direction we are moving toward and the direction we are moving away from. Satellites detecting this temperature shift verified that our galaxy was indeed racing through space at the calculated velocity. This confirmation raised new questions. What could create such an enormous gravitational pull? How massive must the structure be? And why did it concentrate in a region we could not observe? Early estimates suggested the Great Attractor contained mass equivalent to tens of thousands of galaxies. Later calculations refined this to roughly 10 quadrillion stellar masses, concentrated in a region perhaps 200 million light-years away. The numbers seemed almost impossible. structures that large should be obvious, even at great distances. Galaxy clusters containing hundreds or thousands of members typically shine brilliantly, easy to detect across cosmic distances. Yet this monster remained invisible, hidden in the one direction where our view was most obscured. A cosmic veil of dust and stars concealed one of the most influential gravitational structures within our local region of the universe. Scientists recognized the need for a method to see through this obscuring screen of starlight and interstellar particles. They required wavelengths capable of penetrating the zone of avoidance. The solution would ultimately come from an unexpected place, using a form of light that our own eyes are unable to perceive. Imagine the certainty of knowing something exists while being permanently unable to see it. You can detect its influence everywhere you look in the sky. You are able to measure its effects with remarkable precision. You can calculate its location with a high degree of confidence. And yet, the object itself remains forever hidden from direct view. This situation perfectly describes the Great Attractor, one of the most compelling and frustrating discoveries in astronomy. Its location is in the direction of the constellations Centaurus and Triangulum, situated approximately 200 to 250 million light-years from Earth. This placement puts it directly behind the most dense part of our own galactic plane, deep within the most opaque section of the Zone of Avoidance. The timing of this cosmic alignment could not have been less fortunate. If the Great Attractor had appeared in any other direction in the sky, telescopes would have successfully mapped its features decades ago. Instead, scientists are forced to work much like detectives, investigating the scene of a cosmic event without being able to examine that scene directly. They must gather indirect evidence from all the surrounding areas. They carefully measure how nearby structures respond to the invisible influence. They build sophisticated models and run simulations to predict what the hidden region must contain. The gravitational effects of this structure extend across enormous distances. Galaxies located up to 400 million light-years away show motion that is consistent with an attraction toward this specific region. The sphere of this influence encompasses thousands of galaxy groups and clusters, all of which are responding to the same gravitational call. Mapping these intricate motions creates a three-dimensional picture of how mass flows through space, converging on this hidden zone. Scientists eventually discovered that the Great Attractor is not a single object, like a giant galaxy or a black hole. It represents, instead, a region of enhanced mass density, a vast concentration of galaxy clusters that are bound together by their mutual gravity. One way to think of it is as a dense knot in the cosmic web, a place where multiple filaments of galaxies intersect and pile up. The mystery only deepened when researchers came to realize the Great Attractor might not even be the ultimate source of all this motion. Further analysis suggested that something even larger could be pulling on the Great Attractor itself. A more distant structure, called the Shapley supercluster, lies beyond the Great Attractor at a distance of 650 million light-years. This even more massive collection of galaxies might be the true source of the gravitational flow we observe. The relationship between these immense structures creates a clear hierarchy of attraction. Small galaxies fall toward larger galaxy groups. Those groups then fall toward clusters. The clusters, in turn, fall towards superclusters. Each level of this cosmic structure pulls on the levels below it, creating a cascade of motion that extends across hundreds of millions of light-years. Our own galaxy sits near the bottom of this gravitational cascade, responding to pulls from multiple directions simultaneously. The Great Attractor exerts the strongest influence on our local motion, but the Shapley supercluster, despite being much farther away, adds its own significant contribution to the pull. The combined effect of these forces is what determines our ultimate trajectory through space. For decades, the Great Attractor remained a kind of ghost, defined by its gravitational fingerprint rather than by direct observation. Scientists could point to where it should be. They could estimate its mass and its extent. They could predict how it should influence nearby galaxies, but they could not see the galaxies it contained or verify their predictions through direct imaging. The breakthrough would require abandoning visible light entirely. Astronomers needed to look at the universe through a different set of eyes. Light behaves differently depending on its wavelength. The familiar rainbow of colors we see represents only a tiny fraction of the full electromagnetic spectrum. Shorter wavelengths include ultraviolet, X-rays, and gamma rays. Longer wavelengths include infrared, microwaves, and radio waves. Each of these wavelengths interacts with matter in its own unique ways. Visible light, the spectrum our eyes evolved to detect, faces a fundamental problem when it encounters cosmic dust. The tiny particles that make up interstellar dust measure roughly the same size as the wavelengths of visible light. When light hits particles of a similar size, it scatters very efficiently. Blue light scatters the most, while red light scatters somewhat less. This scattering removes light from its original path, preventing it from reaching our telescopes. The effect compounds over distance. Light traveling through just a few light years of dust might lose some of its brightness, but would still remain detectable. However, light traveling through thousands of light years of dust, as is required to see through the galactic plane, gets almost completely absorbed or scattered away. Even the brightest galaxies become invisible. Astronomers discovered that longer wavelengths behave differently. Infrared light, with wavelengths 2 to 10 times longer than visible light, scatters much less efficiently from these same dust particles. It is useful to think of it like throwing a baseball at a chain-link fence versus throwing a much larger beach ball. The baseball might slip through the gaps in the fence that would easily stop the larger ball. Similarly, longer wavelength light can effectively weave around the dust particles that would otherwise block shorter wavelengths. Radio waves extend this advantage even further. With wavelengths measuring centimeters or even meters, radio emissions can pass through dust clouds almost entirely unaffected. The particles of dust are simply too small to block or scatter such long wavelengths effectively. As a result, radio telescopes can see through the galactic plane as if the dust did not even exist. This revelation transformed how scientists approached the zone of avoidance. Instead of fighting a losing battle with optical telescopes, they could switch their focus to infrared and radio observations. The universe would look quite different at these wavelengths. Stars that shine brightly in visible light often appear dim in radio waves. Galaxies might be faint in the infrared, but reveal themselves through the radio emissions from their neutral hydrogen gas. This new strategy required accepting a trade-off. Infrared and radio telescopes typically cannot achieve the same sharp resolution as optical instruments. Images from them appear blurrier, and details are harder to resolve. Identifying individual galaxies in crowded fields becomes more challenging. But the crucial point is that the galaxies become visible at all, which represented a massive improvement over the previous condition of complete blindness. Different wavelengths also reveal different aspects of galactic structure. The signature of infrared light can be used to follow starlight that dust has first absorbed and then re-emitted into space. In a similar way, radio waves are able to sense neutral hydrogen, which is the most plentiful element known to exist, because it releases a distinct signal at a wavelength of 21 centimeters. By integrating observations made across multiple wavelengths, scientists could begin to assemble a far more comprehensive view of what was concealed within the zone of avoidance. The necessary technology for harnessing these wavelengths developed gradually over many decades. For instance, the first infrared detectors had to be cooled to exceptionally low temperatures, a crucial step to keep thermal noise from drowning out the faint signals from deep space. At the same time, radio telescopes demanded immense collecting surfaces to capture a sufficient signal. Both of these technologies saw consistent progress throughout the latter part of the 20th century. By the 1980s and into the 90s, new surveys utilizing both infrared and radio frequencies started to uncover galaxies in areas that had previously been considered devoid of matter. These initial discoveries served to validate what many researchers had already suspected. The zone of avoidance was, in fact, far from empty. The field of radio astronomy brought about a revolution in our capacity to investigate this hidden cosmos. While optical instruments found it difficult to see through even moderate concentrations of dust, radio telescopes could peer directly through the densest parts of the galactic plane. This technique is based on detecting the natural radio emissions from celestial sources, with a particular focus on the signal originating from neutral hydrogen atoms. As the simplest and most common element in the universe, hydrogen is found all through galaxies in both its atomic and molecular states. A neutral hydrogen atom is composed of a single proton and one electron. In certain conditions, that electron is capable of flipping its spin orientation, which releases a very small quantity of energy as a radio photon with a precise wavelength of 21 centimeters. An individual atom undergoes this flip only rarely, perhaps just once in every 10 million years. However, galaxies are home to billions upon billions of these hydrogen atoms. With such a vast population, their cumulative emission becomes a signal that is readily detectable for sensitive radio telescopes. The 21 centimeters line stands out with brightness and clarity in radio spectra, offering a dependable method for locating galaxies even when their starlight is completely blocked from view. The effectiveness of this approach lies in the fact that radio waves are entirely unimpeded by dust. A galaxy could be rendered completely invisible at optical wavelengths, totally obscured by intervening material, and yet it might still shine with great brilliance at radio frequencies. Its hydrogen emission can travel across thousands of light-years of dust without any loss of strength, reaching our telescopes as if no barrier were present. Radio observations also offer another vital benefit. The frequency of the signal that is detected can tell us about a galaxy's velocity. When a galaxy is receding from our position, its radio emissions are shifted towards slightly lower frequencies. Conversely, if it is moving toward us, the frequencies are shifted higher, a phenomenon analogous to the redshift of visible light. This Doppler shift enables an exact measurement of how quickly each galaxy is moving and in which direction it is traveling. By the 1990s, a number of radio surveys had begun the work of systematically charting the zone of avoidance. The Parkes Radio Telescope in Australia carried out wide-ranging searches, meticulously scanning the southern sky for the telltale signature of hydrogen emission. These surveys successfully identified hundreds of galaxies that had never been catalogued before, filling in the voids where optical surveys had registered nothing. Every single detection yielded essential information. The position revealed where the galaxy was located on the sky. The brightness of the radio signal was an indicator of how much neutral hydrogen the galaxy contained, and the shift in frequency disclosed its velocity and, by extension, its distance. When taken together, these measurements empowered scientists to map out the three-dimensional architecture of this hidden part of the universe. The data brought something extraordinary to light. The zone of avoidance was not just a random scattering of isolated galaxies. Instead, distinct patterns began to take shape. Galaxies were seen to group together into clusters and form vast walls, much as they do in the more thoroughly studied regions of the cosmos. Filamentary structures were observed stretching across this concealed area, linking up with known structures on either side of the galactic plane. What was most significant, however, was that radio observations started to unveil what was lurking in the direction of the Great Attractor. The data showed multiple clusters of galaxies concentrated precisely in the region where theoretical calculations had predicted that massive structures had to exist. One of the closest and most notable of these structures was identified as the Norma cluster, situated approximately 200 million light-years away. Even so, radio astronomy was not a complete solution. Its resolution was still limited when compared to optical imaging. This made it challenging to distinguish individual galaxies in fields that were extremely dense. Some areas were so heavily obscured that even radio waves could not penetrate them, but the technique represented the first genuine breakthrough in mapping the zone of avoidance. Scientists soon recognized the need to pair radio observations with another powerful method. Infrared surveys could supply complementary data, revealing different facets of the hidden galaxies. Infrared astronomy thus opened another portal into the zone of avoidance, offering capabilities that radio telescopes could not provide. Whereas radio waves are excellent for detecting hydrogen gas, infrared light traces the stars themselves. Galaxies produce a tremendous amount of infrared radiation, which makes them luminous targets for telescopes with the right equipment. The infrared part of the spectrum covers wavelengths from just beyond visible red light all the way to the edge of microwave radiation. Near-infrared, with wavelengths between 1 and 5 microns, can penetrate dust with reasonable success while still showing stellar populations. Mid-infrared, which extends from 5 to 30 microns, highlights warmer dust and areas of star formation. Far infrared reaches to even longer wavelengths, allowing for the detection of the very coldest dust within galaxies. The earliest infrared surveys relied on relatively simple detectors, which produced catalogues of bright infrared sources across the sky. The Infrared Astronomical Satellite, or IRAS, which was launched in 1983, mapped the entire sky at infrared wavelengths for the very first time. Its resulting catalogue listed hundreds of thousands of sources, and among them, were many galaxies concealed within the zone of avoidance. Researchers devised methods to differentiate galaxies from stars in these infrared catalogues. Stars and galaxies radiate infrared light with differing spectral properties. By analyzing the brightness at several different infrared wavelengths, it became possible to determine which sources were more likely to be distant galaxies as opposed to foreground stars. This color selection method turned out to be remarkably successful. A major advance in sensitivity and coverage came with the 2-micron all-sky survey, which was conducted from 1997 to 2001. This project used dedicated telescopes in both Arizona and Chile, ultimately mapping 99.998% of the celestial sphere in 3 distinct near-infrared bands. The resulting catalogue was immense, listing more than 300 million sources, a figure that included hundreds of thousands of galaxies. This survey proved to be a revolutionary moment for exploring the zone of avoidance. Vast cosmic regions that seemed nearly empty in optical views suddenly came alive, revealing dense populations of galaxies. The project successfully detected galaxies as faint as the 13th magnitude at infrared wavelengths, a sensitivity corresponding to quite distant cosmic systems. Although it did not reach the depths of the best optical surveys in unobscured parts of the sky, the progress it represented for these hidden regions was enormous. Subsequent surveys would push these boundaries even further. The Vista Variables survey, utilizing a large infrared telescope in Chile, initiated a project to map the galactic plane with unprecedented detail. Beginning in 2010, this effort specifically focused on the areas most heavily concealed by dust, employing long exposure times to find faint galaxies that had remained invisible to all prior searches. The Vista survey ultimately produced catalogues that identified over 170,000 galaxies within the zone of avoidance. The great majority of these were being identified for the very first time. This data uncovered an intricate cosmic structure that had been concealed behind the plane of our galaxy. Galaxy clusters, vast walls, and long filaments materialized in regions that astronomers had previously considered impenetrable. A powerful synergy was achieved by combining infrared and radio observations. Radio telescopes could detect neutral hydrogen, which in turn revealed a galaxy's velocity and its reservoir of gas. At the same time, infrared telescopes imaged the stellar populations, showing the overall structure and mass of these systems. Used together, these two methods painted a far more comprehensive picture of the hidden galaxies. The James Webb Space Telescope, launched in 2021, brought unparalleled infrared capabilities to this challenge. By operating at longer mid-infrared wavelengths and achieving much higher resolution than any previous infrared mission, this telescope can spot extremely faint and distant galaxies, even through a heavy veil of obscuration. Its early observations powerfully demonstrated this capability, revealing structure within the zone of avoidance with a clarity never before seen. Despite these incredible advances, significant challenges still exist. Even infrared light is unable to pass through the very densest clouds of dust. Certain regions near the galactic center remain fundamentally opaque at nearly all wavelengths, with the exception of radio waves. Nevertheless, the combination of infrared and radio astronomy has successfully opened up roughly 90% of the previously hidden sky to observation. The first major discovery to emerge from these techniques occurred decades ago, with the revelation of 2 giant galaxies hiding in what was essentially plain sight. In 1968, the Italian astronomer Paolo Maffei made a find that sent a shock through the astronomical community. He had been using infrared photographic plates and detected 2 large, bright galaxies in the constellation Cassiopeia, situated deep inside the zone of avoidance. These galaxies were massive, luminous, and, in cosmic terms, very close to us. And yet, they had managed to evade detection throughout centuries of optical astronomy. This discovery demonstrated just how completely cosmic dust could conceal even enormous, nearby galaxies. Maffei 1 and Maffei 2, as the galaxies came to be known, are located approximately 10 million light-years from Earth. At such a distance, they are considered among our closest galactic neighbors, comparable to well-known galaxies like Andromeda. Optical telescopes, however, saw almost nothing at their positions. The intervening dust absorbed and scattered their starlight so effectively that they appeared as little more than faint, indistinct smudges, if they were visible at all. It was infrared photography that unveiled their true forms. Maffei 1 presented itself as a massive elliptical galaxy, one of the largest in our local cosmic neighborhood. Its total mass was calculated to be more than 100 billion times that of our Sun, making it a true giant. Maffei 2 displayed the classic structure of a barred spiral galaxy, with distinct arms winding out from an elongated central bulge. The discovery served to prove several critical points. First, it confirmed that major structures could indeed be hidden within the zone of avoidance, staying undetected despite their immense size and proximity. Second, it showed that infrared observations were an effective tool for revealing these hidden structures. And third, it meant that the existing catalogues of nearby galaxies were incomplete, very likely missing other significant objects in these obscured areas. Follow-up observations were conducted to study both galaxies in greater detail. Through spectroscopy, their distances were confirmed, and their motion through space was measured. Maffei 1 is moving toward us at a speed of roughly 66 kilometers per second, while Maffei 2 is receding at about 80 kilometers per second. Both galaxies also show signs of past interactions with companions, as they appear to have disrupted smaller satellite galaxies that orbit them. Scientists began to debate whether the Maffei galaxies should be considered part of the local group, the cluster of about 80 galaxies that includes our own Milky Way and Andromeda. Their distances place them right near the boundary of this group. Some researchers made the case that they should be classified as members, but others proposed that they were part of a separate, nearby cluster of their own. The question itself underscored just how incomplete our understanding remained, even of our most immediate cosmic surroundings. The Maffei discoveries acted as a catalyst, inspiring new, systematic searches for hidden galaxies using infrared techniques. The logic was simple. If two giant galaxies could remain unseen, so close to home, what else might be lurking in the zone of avoidance? The decades that followed saw a growing effort dedicated to infrared surveys of these obscured regions, a process that gradually began to fill in the gaps on our cosmic maps. As infrared technology improved, it enabled the detection of ever fainter and more distant galaxies. Each technological advance revealed more of the hidden structure. By the 2000s, catalogues listed thousands of galaxies in regions that had previously been considered empty. The zone of avoidance was thus transformed from an impenetrable barrier into an observational problem that was challenging but ultimately solvable. The Maffei galaxies, however, were only the beginning. Much larger structures were still waiting to be found, concealed behind even thicker curtains of dust. These structures would eventually prove essential to understanding the large-scale organization of the universe, as well as the mysterious motion of our local group toward the Great Attractor. The truly significant breakthrough would arrive in the 21st century, when new radio telescopes achieved a level of sensitivity and coverage that far surpassed anything available before. In South Africa, one of the most powerful radio telescope arrays ever built is now in operation. This is the Meerkat telescope, which consists of 64 individual radio dishes, each one measuring roughly 43 feet across, all working in unison as a single, giant instrument. Situated in the remote Karoo Desert, far from sources of radio interference, Meerkat attains a sensitivity and resolution that are transforming the field of radio astronomy. In 2024, scientists published the results from Meerkat observations of the Vela supercluster region, which is one of the most heavily obscured sections of the zone of avoidance. The survey spanned an area of approximately 240 square degrees of the sky, a patch larger than 1,000 full moons combined. The primary objective was a systematic mapping of all galaxies within a specific region by observing their neutral hydrogen emissions at 21 centimeters, and the outcome far surpassed what was anticipated. The Meerkat telescope detected a total of 719 galaxies inside the survey area. Remarkably, fewer than a third of these cosmic islands had ever been documented before in any survey at any wavelength. The vast majority, numbering over 500 galaxies, were making their debut in astronomical catalogues. Every single one of these detections provided essential information regarding its location, speed, and overall gas mass. What emerged from the data was an intricate cosmic architecture that had been concealed behind the plane of our own galaxy. Galaxies were observed gathering in dense clusters and stretching out along filamentary structures, vast voids became apparent where the density of galaxies fell below the cosmic average. Immense walls of galaxies, extending for tens of millions of light years, were seen connecting previously identified structures on opposite sides of the zone of avoidance. The most significant finding, however, was the confirmation of the existence and sheer scale of the Vela supercluster itself. This colossal structure, which had only been suspected based on earlier, incomplete surveys, came into clear focus within the Meerkat data. The supercluster spans an area of roughly 25 by 20 degrees on the sky and is located approximately 870 million light-years away. Its total mass is estimated to be over 1,000 times that of our entire Milky Way galaxy. It is believed that the Vela supercluster plays a significant role in the movement of the local group towards the Great Attractor region. Current calculations indicate its gravitational pull contributes at least an additional 50 kilometers per second to our own velocity. When considered alongside the Great Attractor and the more distant Shapley supercluster, these enormous structures generate a complex gravitational field that pulls our galaxy and its neighbors through the cosmos. The observations from Meerkat successfully traced cosmic structure across multiple scales. Individual galaxy clusters materialized as dense concentrations within the dataset. These clusters were in turn linked by filaments, forming a pattern reminiscent of a cosmic web. There were also regions designated as voids, which appeared as areas with very few detections, though astronomers have noted that some of these apparent voids could simply be zones where dust obscuration is still too thick, even for radio observations. The survey pinpointed specific formations within the Vela supercluster's domain. The Hydra Wall, a known large-scale structure, was seen clearly in the data for the first time across its full, uninterrupted length through the zone of avoidance. Before this, astronomers had only been able to glimpse portions of this wall as it emerged from the obscured region. The Meerkat observations demonstrated that it continues smoothly across the galactic plane, confirming it as a single, coherent entity. Located deep in the core of the Vela supercluster, another wall is formed by multiple dense galaxy clusters that also traverse the zone of avoidance. These clusters are the richest and most massive components of the supercluster. Their collective gravity holds sway over the local cosmic neighborhood, shaping the motion of galaxies across hundreds of millions of light years. The Meerkat survey is merely an initial systematic map of this area, with follow-up observations planned to investigate fainter galaxies and more remote structures. But the existing data already shows how modern radio telescopes can pierce the obscuring veil of the zone of avoidance, unveiling a cosmic landscape that has remained hidden throughout all of human history. Yet, discovering even 700 new galaxies is only a glimpse of what lies behind our galaxy. At a distance of 870 million light-years from Earth, concealed by the densest part of our galaxy, resides one of the largest structures ever found in our cosmic vicinity. The Vela supercluster measures approximately 385 million light-years along its major axis and 300 million light-years on its minor axis. To traverse such a structure even at the speed of light would take hundreds of millions of years. This supercluster was unknown until its discovery was announced in 2016, following an analysis of thousands of galactic spectra. The research team had meticulously measured the positions and velocities of galaxies that were partly visible on either side of the zone of avoidance. They found definitive proof that these galaxies were all part of a single, enormous structure that stretched across the hidden region. The scientists involved described their work as uncovering a terra incognita, likening it to a great, uncharted continent in the nearby universe, whose full outline they were only just beginning to trace. This analogy effectively conveys the magnitude of the challenge. Much like early cartographers, who could only map coastlines without knowing what lay inland, astronomers could detect the periphery of the Vela supercluster, while its core remained obscured by impenetrable dust. Superclusters are the largest gravitationally influenced structures known in the universe. They are composed of multiple galaxy clusters, all bound together by their mutual gravity and arranged along filaments and walls that can span hundreds of millions of light-years. The most renowned example is the Shapley supercluster, situated 650 million light-years away and containing dozens of massive galaxy clusters. The Vela supercluster is thought to be comparable in mass to Shapley, positioning it as one of the most massive structures in our part of space. Some calculations propose it holds a mass equivalent to 1,000 Milky Way galaxies, which is concentrated mainly within about 20 major galaxy clusters. These clusters act as the dense nodes where the supercluster's gravitational pull is at its most powerful. Its location directly behind the galactic plane allowed it to remain undetected, despite its immense size and relative proximity. Had the Vela supercluster been situated in any unobstructed part of the sky, telescopes would have catalogued it decades ago. Its position in the deepest section of the Zone of Avoidance kept it a secret until recent surveys using infrared and radio wavelengths began to systematically chart these obscured regions. The discovery of the Vela supercluster also helps to explain observed patterns in the motion of galaxies in our cosmic neighborhood. Simulations of how large-scale structures form predict that massive superclusters should exist at particular intervals, creating a web-like pattern that permeates the universe. The Vela supercluster fills a void in this pattern, appearing precisely where theoretical models had suggested a large object should be. The supercluster is comprised of two primary components. A wide primary wall contains the bulk of the structure's mass and stretches across the zone of avoidance at a relatively constant distance. A secondary wall seems to merge with the primary one at an angle, creating a complex, three-dimensional formation. Together, these two walls establish the supercluster's overall shape and size. Within these walls, individual galaxy clusters show up as dense concentrations of matter. Each of these clusters can contain hundreds or even thousands of galaxies, all gravitationally bound together in a relatively compact area. These galactic groupings trace the lines of cosmic walls, their placement recalling beads threaded on a string. They adhere to the invisible framework of dark matter that dictates the form of the universe's grandest structures. The gravitational reach of the Vela supercluster is immense, stretching far past what can be seen. Its pull is perceptible to galaxies across distances of hundreds of millions of light-years, as the supercluster's incredible mass influences their motion. Some studies propose that it is a major factor in the peculiar velocity of our own local group, contributing to the gravitational tug from the Great Attractor and the Shapley supercluster. Charting the precise architecture of the Vela supercluster will demand ongoing observation. Its central areas are still not well understood, as thick curtains of cosmic dust obscure the view, preventing even infrared instruments from cataloguing every galaxy within. In time, more advanced telescopes will help to resolve these remaining mysteries. But the question arises of how astronomers can possibly find galaxies that they are unable to see. A galaxy can give away its location through the faint radio signature of its hydrogen atoms. This specific emission can pass cleanly through cosmic dust that blocks all other forms of light, carrying its message across vast cosmic distances to our telescopes. The process itself begins at the smallest scale, within the atom. A neutral hydrogen atom is composed of one proton with a single electron in orbit around it. Each of these particles has a quality known as spin, which generates a minute magnetic field. The magnetic fields of the proton and electron can exist in one of two states relative to each other. When their alignment is parallel, the atom holds a tiny bit more energy than when their alignment is anti-parallel. Every so often, an atom in this higher energy state will spontaneously transition to the lower energy one. In doing so, the atom sheds its surplus energy by emitting a photon in the radio part of the spectrum. This photon has a very specific wavelength of 1 centimeters, a figure determined by the precise energy gap between the two spin states. For any single atom, such a transition is a rare event. An average atom of hydrogen might take 10 million years to undergo this spontaneous flip. Galaxies, however, possess hydrogen on a scale that dwarfs any terrestrial comparison. A standard spiral galaxy contains hydrogen gas equivalent to billions of suns, spread throughout a disk that extends much farther than its visible stars. With such a colossal number of atoms, their combined radio emission becomes significant. Trillions upon trillions of hydrogen atoms make this transition every second, generating a continuous signal of 21 centimeter photons. Radio observatories can pick up this emission as a distinct spectral line that stands out clearly from background interference. The brightness of this signal tells astronomers how much neutral hydrogen a galaxy holds. A strong emission points to a wealth of gas, which is characteristic of spiral galaxies that are actively forming stars. A weaker signal implies a scarcity of gas, a feature common to elliptical galaxies that used up their star-forming fuel in the distant past. By gauging the total emission, astronomers can calculate a galaxy's gas mass with good accuracy. The frequency of the signal provides another layer of vital information. The Doppler effect comes into play here. If a galaxy is approaching us, its radio waves are compressed to slightly higher frequencies. Conversely, if it is moving away, the waves are stretched to lower frequencies. The degree of this frequency shift reveals the galaxy's exact speed along our line of sight. From this velocity, its distance can be inferred through the principle known as Hubble's law. Due to the expansion of the universe, galaxies that are farther away from us are receding more quickly. Measuring this recession speed allows for a reliable estimate of distance. This method, known as redshift distance estimation, is dependable for galaxies beyond roughly 30 million light-years, where cosmic expansion is the dominant motion. Even the width of the emission line contains useful data. Since galaxies rotate, one side moves toward us while the other moves away. This motion spreads the observed frequencies, which broadens the spectral line. Galaxies that rotate quickly produce wide lines, whereas slow rotators create narrow ones. The known link between rotation speed and galactic mass enables scientists to estimate the total mass, which includes dark matter. Today's radio telescopes are capable of detecting this hydrogen signal from galaxies that are billions of light-years distant. While surveys of the Zone of Avoidance are aimed at closer objects, the Meerkat observations that uncovered 719 galaxies in the Vela region were receiving signals that had travelled for hundreds of millions of years, bearing news of galaxies as they were when Earth was much younger. This technique does have its constraints in some scenarios. For a galaxy to be detected, it must have neutral hydrogen. Elliptical galaxies, having converted the majority of their gas into stars long ago, are often too faint to see or are entirely invisible in hydrogen surveys. The emission from extremely remote galaxies is redshifted so much that it can shift beyond the frequencies that radio telescopes are designed to observe. And in some cases, extremely dense dust can absorb even radio waves. Despite these challenges, mapping hydrogen emissions has transformed our capacity to explore the Zone of Avoidance. It offers the only dependable method for systematically charting the most heavily obscured parts of the sky, revealing galaxies that cannot be seen in any other wavelength. The information gathered from these surveys must be analysed with great care to separate genuine galactic signals from equipment noise and other forms of interference. Investigating invisible cosmic structures necessitates indirect approaches and clever reasoning. Researchers cannot simply aim a telescope at the great attractor to capture an image of it, as they could with a quasar or a nearby nebula. Instead, its characteristics must be deduced from its effects on the space around it. The main technique is to map the velocities of galaxies over an enormous area. The total velocity of any galaxy is a combination of its motion from cosmic expansion and the influence of local gravity. By measuring the speeds of many galaxies and subtracting the motion expected from expansion, scientists can pinpoint areas where gravity is drawing galaxies toward a hidden concentration of mass. It is similar to spotting a whirlpool by observing leaves on a pond. While the underlying current is invisible, the movement of the leaves shows where the water is swirling. In the same way, galaxies serve as tracers, with their movements mapping out the unseen gravitational field. These measurements depend on spectroscopy, which is the analysis of light to ascertain precise velocities. When astronomers study a galaxy's spectrum, they find distinctive patterns of emission and absorption lines at very specific wavelengths. The specific patterns observed in a galaxy's light are a direct result of the elements that make up its stars and gas, with elements such as hydrogen, helium, and oxygen, each producing a unique spectral signature. When a galaxy has a velocity relative to our own, these spectral features all shift in unison. The amount of that shift corresponds directly to the galaxy's speed. A galaxy moving away from us will exhibit a redshift, where its light is stretched to longer wavelengths, while one moving toward us displays a blue shift, with its light compressed to shorter wavelengths. Astronomers can determine a galaxy's radial velocity with remarkable precision, often down to a few kilometers per second, simply by measuring the magnitude of this shift from the pattern's known stationary positions. The process of gathering velocity data for thousands of galaxies allows for the construction of a three-dimensional map of cosmic motion. Every individual measurement contributes a single data point, indicating how a particular galaxy is moving at a specific point in space. When thousands of these measurements are combined, grand, large-scale patterns begin to emerge. Areas where galaxies appear to be converging are telltale signs of significant mass concentrations drawing them inward, while regions where they are moving apart suggest the presence of vast cosmic voids. When studying areas concealed by the Zone of Avoidance, scientists are unable to directly measure the velocities of galaxies within the obscured region itself. Their approach, instead, is to measure the movements of galaxies at the visible edges and then deduce what must lie hidden in the center. An intriguing detail is that if galaxies on all sides of such a veiled area are moving toward it, it strongly implies that an object of immense mass must be lurking within that concealed space. To help interpret these observations, researchers turn to computer simulations. They build virtual models of the universe, populating them with galaxies that are subject to the laws of gravity. By allowing these simulations to progress through time, they can observe how cosmic structures form and how galaxies move in reaction to different arrangements of mass. The key is to compare the motion patterns generated by the simulation with the patterns actually observed in the sky, which allows them to pinpoint which distributions of mass most accurately reflect reality. This very technique proved successful in uncovering the approximate location and mass of the Great Attractor, even though the structure itself remained completely invisible to telescopes operating at optical wavelengths. The calculations indicated that to account for the observed galactic motions, there had to be a concentration of matter equivalent to tens of thousands of galaxies, situated approximately 200 million light-years from us in the direction of Centaurus. Subsequent observations using infrared and radio telescopes validated these predictions, detecting clusters of galaxies in the precise location that had been forecast. Among these, the Norma cluster emerged as one of the closest and most significant structures within the Great Attractor region, its position and mass aligning with what had been predicted. As astronomical surveys became more sensitive, other clusters were also revealed, slowly assembling a more complete portrait of the entire structure. Another powerful technique employed by astronomers is gravitational lensing. Extremely massive structures warp the fabric of space around them, which in turn causes light from more distant objects to travel along curved trajectories. This effect can create distorted, magnified, or even multiple images of these background sources. By carefully analyzing these optical distortions, astronomers are able to map the distribution of mass in the foreground structures, including mass that does not emit any light at all. What makes lensing so useful is that it works even when the lensing object itself is obscured by dust. As long as the background sources are visible, the mass distribution in the foreground reveals its presence through its gravitational influence on the paths of light. This approach has been instrumental in detecting concentrations of dark matter and has helped to map the masses of galaxy clusters located in obscured cosmic regions. Observations in the X-ray spectrum offer yet another avenue of investigation. The hot gas that exists in the space between galaxies emits X-rays, and massive galaxy clusters gravitationally trap vast quantities of this gas, transforming them into luminous X-ray sources. Because X-rays can penetrate cosmic dust more effectively than visible light, they allow for the detection of some clusters even in regions that are partially obscured. It is the combination of all these techniques that ultimately paints a comprehensive picture. Velocity measurements reveal where mass is concentrated. Lensing maps its precise distribution. X-ray observations locate the hot gas. Infrared surveys capture images of the stellar populations, and radio surveys detect neutral hydrogen. Each method provides a unique piece of information, and when used in concert, they overcome the limitations inherent in any single approach. The Great Attractor gradually relinquished its secrets as scientists applied this multi-wavelength, multi-technique strategy, transforming what was once a mysterious, invisible force into a mapped structure with identifiable components. At a distance of 220 million light-years, in the very direction our own galaxy is hurtling through space, lies the Norma cluster. This enormous collection of galaxies stands as the nearest and most accessible component of the Great Attractor's vast structure. Although it remains concealed behind a considerable veil of cosmic dust, the Norma cluster has been investigated more extensively than any other part of this enigmatic region. The cluster itself is composed of hundreds of galaxies, all gravitationally bound within a volume that stretches approximately 10 million light-years across. At its core are several giant elliptical galaxies, each one home to hundreds of billions of stars. Orbiting these colossal galaxies are thousands of smaller spiral and irregular galaxies, all navigating the cluster's powerful gravitational field. The space between the galaxies in the cluster is filled with a superheated gas known as the intracluster medium. This medium reaches temperatures of tens of millions of degrees, heated by the immense energy released as galaxies travel at high velocities through the cluster's deep gravitational well. At such extreme temperatures, this gas emits a profuse amount of X-rays, which causes the Norma cluster to appear as a bright object in X-ray observations. In this way, despite the dust that blocks optical light, X-ray telescopes are able to map the cluster's overall structure, revealing both its physical extent and the distribution of its mass. The presence of this hot gas effectively traces the cluster's gravitational potential, highlighting the areas where mass is most heavily concentrated. Studies have determined that the Norma cluster contains a total mass equivalent to approximately 10 trillion stellar masses, a figure that accounts for both its visible matter and its dark matter. The cluster's own velocity, when measured against the background of cosmic expansion, helped to confirm its place as a part of the Great Attractor. What stands out is that measurements revealed the Norma cluster has a peculiar velocity of just 44 kilometers per second, a speed far lower than one would anticipate if it were being pulled toward a more distant concentration of mass. This low velocity suggests that the Norma cluster is situated very near the heart of the Great Attractor structure itself, moving quite slowly in relation to the overall gravitational center. Further surveys revealed additional galaxy clusters in the vicinity. The Centaurus cluster, Pavo cluster, and several others came into view through infrared and radio observations, all occupying the same general area of the sky and lying at comparable distances. Collectively, these clusters constitute what astronomers refer to as the Norma Wall, or Great Attractor Wall, a vast, filament-like structure that stretches across the Zone of Avoidance. This cosmic wall extends beyond the obscured region, linking up with visible structures on either side of the Milky Way's plane. If one were to follow this wall in a particular direction, it would lead to concentrations of galaxies located in the constellation Centaurus. In the opposite direction, this filament reaches toward the constellation Vela, where it links up with the Vela supercluster at an even greater distance. This observable continuity serves as confirmation that the formations identified within these obscured skies are indeed authentic connections to the greater cosmic web. The individual galaxies that make up the Norma cluster display traits that are typical for such dense environments. A great number of them have the appearance of red elliptical galaxies, a state they reached after either using up their reserves of gas for star formation or having it stripped away by interactions with neighboring galaxies. The environment of a cluster is known to pull gas from galaxies as they fall inward, which halts the birth of new stars and gradually transforms spiral galaxies into ellipticals over billions of years. Despite its central role in our understanding of the Great Attractor, the Norma cluster remains a profoundly difficult object to study in detail. The thick veil of dust makes it impossible to get clear optical images of its member galaxies. To gather enough light from these faint, hidden sources, the technique of spectroscopy demands extremely long integration times. As a result, only the most luminous members of the cluster can be investigated individually with our current technology. The cluster's position, deep within the Zone of Avoidance, means it has not received the same level of attention as more famous clusters like Coma or Virgo, which are situated in clear patches of the sky and have been subjects of extensive research. And yet, the Norma cluster arguably holds a more significant position in our own cosmic neighborhood, as it lies at the very heart of the gravitational structure that is pulling our local group across the cosmos. Future observations using more powerful infrared telescopes promise to gradually lift the veil on the Norma cluster and its galactic neighbors. The James Webb Space Telescope has the capability to image individual galaxies within the cluster, allowing for studies of their internal structures and stellar populations. In parallel, next-generation radio arrays will be able to map the neutral hydrogen throughout this area, tracing the distribution of gas and the true masses of the galaxies. While a deeper comprehension of the Norma cluster is key to resolving the mystery of the Great Attractor, the narrative expands far beyond this single formation. In 2014, a team of astronomers announced a finding that fundamentally rewrote our cosmic address. The Milky Way, it turns out, is not simply an isolated entity drifting through the void, nor does it belong to just a small local group of galaxies. We now know that we exist as one minuscule part of a colossal supercluster, an immense structure containing over 100,000 galaxies and stretching across 500 million light-years of space. The scientists gave this structure the name Laniakea, a Hawaiian word that translates to immense heaven or immeasurable heaven. The name beautifully captures both the sheer scale of the structure and the profound revelation it represented. For the entirety of human history, we were completely unaware that we lived inside this cosmic giant. Laniakea represents a new way of defining a supercluster, different from previous methods. Instead of merely locating regions with a high concentration of galaxies, the researchers focused on mapping cosmic flows. They measured the movement of galaxies through space, which allowed them to trace the gravitational currents that bind together vast stretches of the universe. This method treats the cosmos as a kind of topographic map where water is flowing, in the same way that rain falling on a mountain range will flow downhill into valleys and basins. Galaxies flow through space toward gravitational low points, or attractors. By charting these cosmic currents for more than 100,000 galaxies, the team was able to identify regions that all drain toward a shared basin of attraction. Laniakea was revealed to be one such basin. Every galaxy throughout this enormous volume is flowing inward toward a common gravitational center. These flows provide a much more meaningful definition for the supercluster's boundaries than simple measurements of distance or density. The edge of the structure is found where the flows begin to diverge, a cosmic watershed, where galaxies start to fall toward different attractors. The Great Attractor is located near the center of Laniakea. It is not positioned at the exact center, but it is close enough to be considered the primary gravitational focus of the entire structure. Galaxies from every direction within Laniakea are flowing toward the region of the Great Attractor, which creates the convergent pattern of motion that has been observed in our measurements. Our own local group is a participant in this grand flow. We are drifting along with the Virgo supercluster, the Hydra Centaurus supercluster, and the Pavo Indus supercluster, all of which are constituent parts of the larger Laniakea. The motion that once seemed so mysterious when it was first detected now fits neatly into a coherent picture of how structure forms on the most immense scales. Laniakea is composed of four major components. The Virgo supercluster, which is home to our local group, forms one of the arms extending out from the center. The central region is formed by the Hydra Centaurus supercluster, which contains the Great Attractor. Extending in other directions are the Pavo Indus and Southern superclusters, which together create a shape resembling a cross when seen from above. The total mass of Laniakea is estimated to be 100 quadrillion times the mass of our Sun, or about 100,000 times the mass of the Milky Way. The vast majority of this mass is in the form of dark matter, the invisible substance that sculpts the gravitational landscape of the universe. Ordinary matter, the material that makes up stars and gas, accounts for only about 15% of the total. What is intriguing is that despite its enormous size, Laniakea is not gravitationally bound. Although its component galaxies currently share common patterns of motion, they are not destined to stay together forever. Cosmic expansion, which is driven by dark energy, is pushing different regions of space apart at a rate that is faster than gravity can pull them together over these vast distances. In the distant future, billions of years from now, the components of Laniakea will drift apart, carried away by this accelerating expansion. This lack of gravitational binding is what separates Laniakea from smaller structures like galaxy clusters. The Norma cluster, for instance, spans about 10 million light-years and will remain gravitationally bound. Its galaxies are destined to stay together indefinitely and will likely merge into a single giant elliptical galaxy over cosmic time. Laniakea, spanning 500 million light-years, is more of a temporary arrangement of matter, a a snapshot of material flowing through an expanding universe. The discovery of Laniakea provided the essential context for understanding the Great Attractor and our motion relative to it. We are not being pulled towards some distant, isolated object. Instead, we are participating in the internal dynamics of a truly enormous supercluster, just one component among many, all engaged in a coordinated gravitational dance. But the story doesn't end there, as Laniakea itself is flowing towards something even larger in the distance. The structure of Laniakea is most clearly visualized in maps that show galactic motion. It helps to imagine looking down upon a vast landscape from a great height, observing rivers and streams as they flow across the terrain toward lakes and oceans. The water naturally defines drainage basins, which are regions where all the precipitation ultimately travels to a single destination. Laniakea operates on a similar principle, but instead of water flowing downhill, it is galaxies flowing along gravitational gradients. To create these cosmic maps, scientists measured the precise velocities of over 100,000 galaxies, employing a variety of observational techniques. To chart the vast movements of the cosmos, astronomers gathered velocity data from a wide range of sources. Bright galaxies in clear patches of sky were measured using optical spectroscopy, while radio observations provided the necessary velocity information for gas-rich spiral galaxies, including many that are typically obscured by the plane of our own Milky Way. By employing various techniques to measure distance, researchers could carefully separate a galaxy's motion caused by the expansion of the universe from its peculiar velocity, which arises from the pull of gravity. The picture that emerged from this velocity field was one of remarkable organization. It became clear that galaxies are not moving through space at random. Instead, they follow distinct patterns, with immense flows converging upon regions of high density and streaming away from the great empty voids. These flows trace the paths of cosmic filaments, which act like celestial rivers, channeling matter into the gravitational basins of clusters and superclusters. Within the structure of Laniakea, several of these major flows are drawn toward the area known as the Great Attractor. Our own local group is part of this cosmic current, approaching from one direction at a speed of 600 kilometers per second. The massive Virgo cluster adds its considerable weight to this inflow, approaching from a different angle. More distant galaxy groups that are part of the larger Virgo supercluster component are also streaming inward. From other directions still, the Centaurus and Hydra clusters contribute their own mass to the convergence. These enormous structures have their origins in the very early universe, where subtle, initial regions of slightly higher density acted as seeds for gravity to begin its work of gathering matter. Over the immense timescales of cosmic history, these slight overdensities grew ever stronger, pulling in surrounding material to sculpt the intricate and complex architecture we observe today. An intriguing detail in these cosmic currents is that they do not point directly at the Great Attractor, but rather slightly beyond it. A more detailed analysis of the data revealed the reason for this offset: the Shapley supercluster. A colossal structure located 650 million light-years away is exerting its own powerful gravitational influence. Even though it is much farther away, Shapley contains even more mass than the Great Attractor, concentrated within dozens of rich galaxy clusters. The ultimate trajectory of our motion is therefore determined by the combined pull of both the Great Attractor and Shapley. Our flow is directed first toward the Great Attractor region, but if the universe were not expanding, our journey would eventually carry us past it and onward toward Shapley. However, the accelerating expansion of the cosmos will ultimately prevent this grand voyage. Distant structures are receding from us faster than we can approach them, which means we will never actually reach the Shapley supercluster. The velocity field also serves to illuminate the very boundaries of Laniakea. The edge of the supercluster's gravitational influence is found where the cosmic flows begin to diverge, moving away from the Great Attractor. Galaxies that lie beyond these boundaries are falling toward different attractors, belonging to different superclusters in the cosmic web. One such boundary separates Laniakea from the Perseus-Pisces supercluster, a large structure located in another part of the sky. Galaxies on our side of this line flow toward the Great Attractor, while galaxies on the far side flow toward the Perseus-Pisces region. This boundary acts as a kind of cosmic watershed, much like a mountain ridge on Earth that separates different river basins. Another boundary divides Laniakea from the Coma supercluster. This particular line runs through the relatively nearby Virgo region, placing some of its galaxy groups within Laniakea and others within the Coma structure. The exact position of this boundary remains somewhat uncertain, as it depends on very detailed velocity measurements. Uncovering the full extent of Laniakea was a monumental undertaking, emerging only after decades of work combining data from multiple astronomical surveys. Early galaxy catalogues provided positions on the sky, but lacked reliable distances. Later, redshift surveys added the crucial velocity information. It was the modern, large-scale structure surveys that finally brought the complete picture into focus, combining positions, velocities, and distances for hundreds of thousands of galaxies and enabling a comprehensive mapping of cosmic flows. What these maps ultimately revealed was a profound truth about the universe. Its structure is organized hierarchically across many different scales. Stars collect into galaxies, galaxies gather into groups and clusters. These clusters, in turn, line up along vast filaments and walls. These larger structures then drain into superclusters like Laniakea, and even the superclusters themselves connect into larger scale patterns that suggest organization on the most immense cosmic scales. Understanding this hierarchy has completely transformed our perspective on the universe. For most of human history, knowing our cosmic location meant little more than understanding that Earth orbited the central star of our solar system. The Copernican revolution placed us in orbit rather than at the center, a humbling but still incomplete picture. The astronomy of the 20th century greatly expanded our address. We learned that our solar system belongs to the Milky Way galaxy, just one among billions scattered through space. We discovered our specific location within that galaxy, about 30,000 light-years from the center in a minor spiral arm. We also identified our galaxy's membership in the local group, a collection of roughly 80 galaxies bound together by gravity. The discovery of Laniakea introduced yet another profound layer to our cosmic address, showing that even the local group is just one small component of a much vaster structure. Writing our full cosmic address now requires listing multiple nested levels of organization, each one larger than the last. The complete address reads something like this: Planet Earth, the third planet orbiting a medium-age star located in the Orion arm of the Milky Way galaxy, a member of the local group of galaxies, which is a component of the Virgo supercluster, belonging to the Laniakea supercluster, which is flowing toward the Shapley concentration in the even larger scale structure of the cosmic web. Each level of this address connects us to larger and larger communities of matter. Earth belongs to a solar system, bound by the gravity of a single star. That system belongs to a galaxy, bound by the gravity of hundreds of billions of stars. That galaxy belongs to a group, the group to a supercluster, and the supercluster to an even larger congregation of structures. Each transition represents a jump in scale by factors of hundreds or thousands. This discovery also clarified why earlier attempts to define our local supercluster had been so confusing. The traditional Virgo supercluster, which was defined by simple proximity to the Virgo cluster, did not represent a coherent gravitational structure. Galaxies that were assigned to it did not all share a common motion or history. Some were falling toward Virgo, while others were moving in different directions. Laniakea corrects this by defining membership based on gravitational flow rather than simple distance. What is so significant is that every galaxy in Laniakea shares a common destiny, at least on short cosmic timescales. They are all flowing toward the same gravitational basin, participating in the same large-scale patterns of motion. This redefinition encompassed 100,000 galaxies within 500 million light-years of Earth. By this new, flow-based definition, all of them now belong to Laniakea. This immense structure is composed of 4 primary subclusters and a great number of smaller groupings, all of which are interconnected by a common trajectory toward the Great Attractor's domain. Gaining this understanding of our position within Laniakea helps to clarify observations that previously seemed perplexing. The local group's movement in the direction of the Great Attractor ceases to be an anomaly, fitting instead, quite naturally, into the supercluster's own internal dynamics. The Virgo cluster's motion along a similar path is now understood as just another element within this same cosmic current. Even very remote structures inside Laniakea exhibit consistent patterns of movement, all directed toward this shared central point. This discovery, however, prompts new questions about what might exist beyond the boundaries of Laniakea. If our own supercluster is flowing toward the Shapley concentration, then what kind of even larger structure could possibly contain them both? It raises the possibility that superclusters might arrange themselves into yet grander systems, each possessing its own coherent patterns of motion. One must wonder how many tiers of this hierarchy exist before we reach a scale where the universe's expansion simply overpowers the pull of gravity. Current observations indicate the presence of at least one additional layer of organization. The Shapley concentration seems to be the gravitational heart of an even vaster system, occasionally called the Shapley attractor, which exerts its influence over a region 1 billion light-years across. Our own drift toward Shapley is simply our participation in the dynamics of this more immense cosmic structure. Ultimately, however, this hierarchical arrangement must come to an end. On scales greater than roughly 1 billion light-years, the expansion of the cosmos overwhelms gravity's force. Structures are unable to form or sustain cohesive movement when the fabric of space itself is stretching faster than gravity can draw matter together. While the observable universe does show faint traces of structure at these enormous scales, they are thought to be residual patterns from the early cosmos rather than gravitationally bound entities. Our cosmic address now extends to the very scale where the influence of gravity wanes and the dominance of expansion begins. We are part of structures that span hundreds of millions of light-years, flowing through the cosmos in motions that will persist for eons before expansion finally prevails, tearing even superclusters apart. The Great Attractor, once a profound mystery, now finds its place within this broader picture as one gravitational hub among many in the hierarchical cosmic web. Some 650 million light-years past the Great Attractor, an even more colossal entity governs the gravitational environment. The Shapley supercluster simply overshadows everything else in our local cosmic vicinity, holding a mass comparable to many millions of galaxies gathered into a fairly compact area. If the Great Attractor pulls on us with a discernible force, the pull from Shapley is truly overwhelming. First identified in the 1980s, the Shapley supercluster presented itself as a remarkable collection of galaxy clusters within the constellation Centaurus. Astronomers discovered more than 24 massive clusters densely packed into a volume just a few 100 million light-years wide. Each of these clusters was home to hundreds or even thousands of galaxies, and their combined presence formed the most dense concentration of matter known in the local universe. Unlike the Great Attractor, which is largely hidden, Shapley is situated just beyond the Zone of Avoidance. Most of the structure is surrounded by clear skies, which allows optical telescopes to map its full extent with great detail. Furthermore, X-ray observations have detected vast quantities of superheated gas permeating the space between the clusters, confirming the supercluster's incredible mass. Its total mass is estimated to be around 10,000 trillion times that of our Sun. Early measurements of Shapley's movement revealed something unusual. The majority of distant structures are receding from us because of cosmic expansion, causing their light to be shifted toward the red end of the spectrum. Shapley, however, displays a smaller redshift than would be expected for its distance, which implies it is moving slightly toward us instead of purely away. This is a clear indicator of a gravitational link between Shapley and our own region of space. Subsequent analysis showed that Shapley's influence on the motion of galaxies extends over enormous distances. Structures as far as 800 million light-years away exhibit velocities that are consistent with being pulled toward Shapley. Its sphere of influence reaches far beyond the supercluster's visible edges, stretching across a significant portion of the observable universe. Detailed mapping of cosmic velocities demonstrated that Shapley, and not the Great Attractor, is the principal source of our peculiar motion. The Great Attractor is itself falling toward Shapley, drawn in by the more distant structure's superior mass. We are pulled toward the Great Attractor, which is in turn pulled toward Shapley, resulting in a cascade of gravitational influence that spans hundreds of millions of light-years. An analogy might be a hierarchy of gravitational wells. Small streams flow into larger streams, which then merge into rivers, all of which eventually flow to the ocean. In a similar way, galaxy groups fall into clusters, and those clusters are drawn into the Great Attractor region, while the Great Attractor itself is falling toward Shapley. Each level in this system governs the motion of the structures beneath it. The Shapley supercluster is home to several of the most massive galaxy clusters known anywhere in the relatively nearby universe. The cluster designated A3558, for instance, contains thousands of individual galaxies and enough hot gas to outshine entire galaxy groups in X-ray light. Within Shapley, multiple clusters of this magnitude are packed closely together. It is their immense combined gravity that creates such a powerful attraction. Some of the clusters inside Shapley are in the process of actively merging, colliding at speeds of thousands of kilometers per second. These cosmic collisions unleash tremendous amounts of energy, heating gas to hundreds of millions of degrees and generating shockwaves that travel through intergalactic space. The sheer violence of these mergers is a testament to the incredible gravitational forces at play. Despite being 3 times farther away than the Great Attractor, Shapley actually contributes more to our peculiar velocity. Calculations indicate that about half of our motion toward the Great Attractor's location is really due to the pull of the more distant Shapley supercluster. The remainder of our motion is caused by the Great Attractor itself, along with other nearby structures. This revelation fundamentally altered the way astronomers perceived our motion through the cosmos. The mystery of the Great Attractor was never about a single, hidden object. Instead, it was about a complex gravitational landscape where multiple massive structures at varying distances combined their influence to pull our local group through space. In this landscape, Shapley represents the single most dominant force, and yet, even the Shapley supercluster does not signify the final step in this gravitational hierarchy. The universe organizes itself through gravity across a multitude of scales, forging a cosmic hierarchy where each level exerts its pull on all the levels below it. To grasp this cosmic hierarchy is to gain a window into how all structure has formed over billions of years, and to understand the fundamental reasons for the motions of galaxies. At the most intimate level of this structure are the individual galaxies, each one a distinct island of matter held in place by its own gravity. Inside them, stars follow stable orbital paths around the galactic center, patterns that can remain unchanged for eons. The primary source of the gravitational cohesion for each galaxy is a surrounding halo of dark matter, which provides the necessary binding force to keep the visible, rotating material from dispersing into space. The next tier in this architecture is composed of galaxy groups. These are looser collections where dozens of galaxies orbit one another, all bound by their shared gravitational field. Our own local group is a classic example of this scale, with the Milky Way and the Andromeda Galaxy as its 2 most massive components, which are on a long-term trajectory to eventually combine. Smaller galaxies move in orbit around these 2 giants, captured within their deep gravitational wells. A significant leap in both size and mass brings us to galaxy clusters. Here, hundreds or even thousands of galaxies are densely packed into regions that can span from 10 to 20 million light-years across. The vast spaces between these galaxies are not empty but are filled with an extremely hot gas, warmed to incredible temperatures by the kinetic energy of galaxies moving through the cluster's immense gravity. When dark matter is factored in, the total mass of these clusters can reach hundreds of trillions of times the mass of our Sun. Extending this hierarchy even further are the superclusters. These colossal formations link numerous galaxy clusters together along immense filaments and walls, weaving patterns that can stretch for hundreds of millions of light-years. Both the Great Attractor and the Shapley supercluster are prominent examples at this scale, each containing dozens of major clusters and a countless number of smaller groups. Every level within this cosmic structure exerts a gravitational pull on the levels beneath it. Galaxy groups are drawn toward nearby clusters, which in turn fall towards superclusters. These superclusters are themselves pulled toward the greatest concentrations of mass in the entire cosmic web. All these motions compound, giving rise to the complex velocity fields that astronomers map when they measure the positions and movements of galaxies. The Great Attractor exerts a powerful pull on our local group, a force that would seem overwhelming on smaller scales. Yet, this force is just one element contributing to our overall motion through the cosmos. The pull from the Shapley supercluster is even stronger, and it is this influence that ultimately governs our long-range trajectory. Other, more distant structures add their own smaller gravitational tugs, further complicating our journey through space. Beyond the Shapley supercluster, it is possible that even larger structures exist. There are some observations that point to mass concentrations at distances approaching 1 billion light-years, which would influence motion on truly vast cosmic scales. One intriguing feature, the cold spot in the cosmic microwave background, might be evidence of a supervoid, an enormous, empty expanse whose gravitational signature effectively pushes surrounding matter away. These grandest of structures test the very limits of what is possible to form within an expanding universe. Gravity needs time to gather matter into such organized systems. The universe's finite age of approximately 13.8 billion years places a natural constraint on how large any structure can become, before cosmic expansion carries the constituent material too far apart for it to ever coalesce. Computer simulations that model the formation of structure replicate this observed hierarchy with astonishing accuracy. When these simulations begin with the tiny fluctuations in density present in the early universe, the virtual matter naturally assembles into galaxies. These galaxies then gather into groups and clusters, which subsequently arrange themselves along the filaments that connect superclusters. The cosmic web is an inevitable result of gravity acting upon what was initially a nearly uniform distribution of matter. What is remarkable is how closely real observations align with these simulations. The measured positions of galaxies, the sizes of clusters, and the velocities of these structures all correspond with the predictions of models built on gravity, dark matter, and dark energy. The hierarchy we see today is simply the natural consequence of cosmic evolution. The picture, however, is complicated at the largest scales by the presence of dark energy. This enigmatic force is causing the expansion of the universe to accelerate, pushing distant structures apart more rapidly than gravity can draw them together. The ultimate fate of cosmic structures is determined by this ongoing competition between gravitational attraction and accelerated expansion. Superclusters like Laniakea exist at a critical scale, where this contest becomes particularly consequential. Smaller systems, such as galaxy clusters, will remain gravitationally bound as their internal gravity is strong enough to overcome local expansion. In the current epoch, however, larger structures can no longer form because expansion triumphs before gravity has sufficient time to assemble the necessary matter. This means that superclusters are transient arrangements that will ultimately be pulled apart as cosmic expansion continues to accelerate. Our motion toward the Shapley supercluster will persist for hundreds of millions of years, but we are not destined to arrive. The accelerating expansion of space will eventually carry Shapley away from us faster than we can approach it, which will ultimately reverse our relative motion. The gravitational hierarchy that currently defines our cosmic path will slowly dissolve as dark energy disassembles even these most massive of structures. This understanding of cosmic structure also helps us address questions about the universe's history and its ultimate fate. Dark matter is a pervasive component of the cosmos, outweighing all ordinary matter by a ratio of roughly 5-1. Despite its prevalence, we are unable to see it directly, detect it with conventional telescopes, or capture it in any laboratory. Our knowledge of its existence comes solely from observing its gravitational effects on visible matter. The structures concealed within the zone of avoidance offer vital clues about how dark matter is distributed throughout space. The most unambiguous evidence for the existence of dark matter is found within galaxy clusters. The visible galaxies and the hot interstellar gas in a typical cluster only make up about 15% of the total mass required to explain the cluster's gravitational power. An unseen, invisible substance must be providing the remaining 85% of the mass. That substance is dark matter. The regions of the Great Attractor and the Vela supercluster are expected to contain tremendous amounts of dark matter, concentrated along the very same filaments and walls where visible galaxies are found. Computer models predict that dark matter forms a vast cosmic web, with dense filaments connecting massive nodes where clusters form. Ordinary matter is then drawn to this dark matter scaffolding, accumulating in places where dark matter is already highly concentrated. Mapping the structures within the zone of avoidance provides a direct test of these predictions. If the simulations accurately model the behavior of dark matter, then the discovery of galaxy superclusters in their predicted locations serves as a powerful confirmation of the dark matter distribution. The Vela supercluster, for instance, was found precisely where models had suggested a massive concentration of dark matter should be, based on the observed motions of galaxies near the edges of that obscured region. The detection of hundreds of new galaxies by the Meerkat telescope provides the specific data points needed to map this dark matter with greater precision. Each newly identified galaxy pinpoints a location where ordinary matter has gathered, thereby signaling the presence of an underlying concentration of dark matter. The arrangement of galaxies across the sky provides a way to trace the invisible architecture of dark matter as it clumps and streams through the zone of avoidance. Another essential layer of information comes from measuring the velocities of these galaxies. Dark matter carves out deep gravitational wells, which in turn dictate how galaxies move through space. By charting the speeds of a great many galaxies, astronomers can reverse engineer the gravitational field, and this field serves as a direct reflection of the dark matter distribution. What makes this technique so powerful is that it works even where thick dust conceals everything in visible light, because velocities can be measured using radio observations of neutral hydrogen. The mass of the Great Attractor region, for example, is estimated to be equivalent to tens of thousands of galaxies, and the vast majority of this mass is dark matter. The galaxies we can see, along with hot gas, make up just a tiny fraction of the total. The rest remains hidden as dark matter particles, exerting a powerful gravitational pull on surrounding structures while being otherwise undetectable. A complete understanding of the total mass distribution depends on accounting for this dominant, unseen component. Dark matter's influence extends far beyond individual clusters. The cosmic web itself is fundamentally a dark matter phenomenon. Simulations have shown that even in a universe without any ordinary matter, dark matter alone would still form the immense filaments, nodes, and voids that we observe. The ordinary matter simply settles into the patterns that dark matter established first. Studying the zone of avoidance helps to constrain the very properties of dark matter. Different theoretical models predict slightly different patterns of distribution and clustering. By comparing these predictions to actual observations, scientists can test whether dark matter is composed of heavy particles, light particles, or something more exotic entirely. The data collected so far tends to support the standard model of cold dark matter, which consists of heavy, slow-moving particles that clump together very efficiently. Some researchers have theorized that dark matter might cluster more or less intensely than standard models predict, and certain discrepancies between simulations and observations on small scales could point to non-standard properties. However, detailed studies of the Great Attractor region reveal clustering that is consistent with cold dark matter predictions, lending strong support to the standard model. The effect of gravitational lensing offers another method for mapping dark matter in obscured areas. Light from extremely distant galaxies that passes near the Great Attractor, or the Vela supercluster, is bent by the gravity of the intervening dark matter. This process creates subtle, telltale distortions in the images of those background galaxies. By analyzing thousands of these distorted images, astronomers can map the dark matter's distribution, even when the lensing structures themselves are completely hidden from view. Future surveys are poised to map dark matter in the zone of avoidance with even greater precision. The upcoming Nancy Grace Roman Space Telescope will perform wide-field infrared surveys, capable of detecting faint background galaxies over huge swaths of the sky. Measuring how the structures within the zone of avoidance lens these background sources will produce exceptionally detailed dark matter maps. Understanding this distribution is important for questions that go far beyond simple mapping. Dark matter dominates the gravitational dynamics of our universe. Knowing where it is concentrated and how it moves is crucial for predicting cosmic evolution, galaxy formation, and the ultimate fate of all cosmic structures. The zone of avoidance, despite its name, is therefore a place of vital observation for understanding the invisible substance that shapes our visible reality. A new chapter in piercing the deepest regions of this obscuration began on Christmas Day 2021 with the launch of the James Webb Space Telescope. This observatory operates in deep space, orbiting a point 1 million miles from Earth, where it can draw constant solar power while its instruments peer into the cold, dark universe. Its mirror, which spans more than 21 feet across, gathers infrared light with unprecedented sensitivity. Webb's capabilities are fundamentally transforming observations of the zone of avoidance. While previous infrared telescopes could detect only the brightest galaxies through the heavy dust, Webb perceives fainter, more distant objects with a clarity that was once impossible. Its mid-infrared instruments are especially effective because they operate at longer wavelengths where dust becomes more transparent, allowing them to penetrate regions that blocked earlier surveys. Early observations have already demonstrated this power. When Webb focused on an area in the zone of avoidance previously thought to be almost empty based on optical catalogues, the resulting images revealed dozens of galaxies crowding the field. Their light had been shifted to infrared wavelengths by dust absorption. Some were just faint smudges, barely rising above the detection limit, while others were massive, brilliant galaxies that had been hiding in plain sight. The telescope's high resolution is critical for resolving individual galaxies in such crowded regions, where older instruments would have seen only a blurred patch. This is particularly important within the zone of avoidance, where countless foreground stars from our own galaxy can confuse the view. Webb can easily separate a distant galaxy from a nearby star based on their different colors and appearances. Even more valuable data is provided by spectroscopic observations. Webb's spectrographs can split the infrared light from an object into its component wavelengths, revealing detailed information about that galaxy's composition, distance, and motion. This capability allows for the precise measurement of velocities for obscured galaxies, adding crucial data points to the velocity field maps. One especially powerful technique utilizes Webb's ability to detect distant galaxies through gravitational lensing. The Great Attractor and Velar supercluster regions contain enough mass to magnify and distort the images of galaxies far behind them. Webb can detect these background objects even when the foreground lensing structures are heavily obscured. A careful analysis of these lensed images reveals the foreground mass distribution in remarkable detail. Webb's observations have already confirmed predictions about structures within the zone of avoidance, finding galaxy clusters right where velocity measurements suggested they would be. The distribution has also matched models based on dark matter simulations. At the same time, unexpected discoveries have emerged, including isolated, massive galaxies in regions thought to contain only small groups. The telescope's sensitivity makes it possible to conduct observations that reach billions of light years through the zone of avoidance. This deep view extends these studies far beyond local structures like the Great Attractor, probing how obscured regions connect to the larger-scale cosmic structures. Distant quasars and galaxy clusters are now visible through the dust, providing new lines of sight to study the intervening material. Nevertheless, even Webb has its limitations. The very densest clouds of dust, particularly those near the center of our galaxy, are still able to block mid-infrared light to some degree. For complete penetration of these regions, radio observations continue to be essential. The Webb telescope, for all its power, is not designed to survey large areas of the sky with speed. Its observations are deep and detailed, focusing intently on small patches of the cosmos, which means that comprehensive maps are built up piece by piece over time, rather than through a single sweeping gaze. To complement Webb's focused approach, future missions are already in development. One of the most anticipated is the Nancy Grace Roman Space Telescope, which is scheduled for launch later in this decade. This observatory will perform wide-field infrared surveys, capturing immense celestial territories that cover thousands of square degrees. While Roman will not be as sensitive as Webb when it comes to individual point sources, its efficiency in mapping vast regions will be unparalleled, allowing it to identify compelling targets for Webb to investigate in greater detail. Meanwhile, infrared telescopes on the ground are also undergoing continuous enhancement. The implementation of adaptive optics systems actively corrects for the distorting effects of Earth's atmosphere, enabling these facilities to achieve a level of resolution at near-infrared wavelengths that rivals that of telescopes in space. Furthermore, a new class of extremely large telescopes is currently under construction, featuring mirrors that measure over 100 feet in diameter. These colossal instruments will gather immense quantities of light, making it possible to study the faintest and most obscured galaxies. The combination of observatories in space and facilities on the ground provides a remarkably powerful toolkit for exploring the zone of avoidance. Each instrument brings its own unique strengths to the task, and together they are piecing together a more complete picture of the hidden universe. Astronomers anticipate that within the next 10 years, they will have successfully detected and catalogued the vast majority of galaxies, even in the most heavily obscured regions. Webb's initial observations have already yielded surprising findings that are challenging established theories. For instance, some of the discovered galaxies appear to be far more massive than models would predict for their given distances. Other galaxies exhibit unusual chemical compositions or peculiar shapes. Every new discovery serves to refine our understanding of how galaxies form and evolve within these cosmic realms that were previously beyond our reach. Even so, it is likely that some areas will remain forever concealed from our view. The most advanced telescopes, present and future, will eventually encounter fundamental physical limits as they attempt to peer through the zone of avoidance. Certain regions are permeated by dust so thick that virtually no wavelength of light can effectively pass through. It is probable that the very densest parts of our galaxy's plane will stay at least partially obscured for the foreseeable future, permanently hiding some portions of the universe from direct observation. The area around the galactic center poses the most extreme observational challenge of all. To look directly toward the heart of our own galaxy is to peer through the maximum possible thickness of the galactic disk. Along this specific line of sight, layer after layer of dust clouds accumulate, stretching across thousands of light years. Even radio waves, which penetrate dust more effectively than other wavelengths, find it difficult to pass through completely. The dimming effect of dust, known as extinction, increases exponentially with the density of the material. If you double the quantity of dust along a line of sight, the light that gets through is reduced by much more than half. Gazing through the galactic center means contending with perhaps 10 times more dust than is found in typical areas of the zone of avoidance. Here, the extinction is so severe that almost nothing can be detected beyond it, except with the most powerful radio observations. Another fundamental difficulty arises from what is known as source confusion. The plane of our galaxy is filled with hundreds of billions of stars. In any given direction through the zone of avoidance, thousands of these foreground stars will appear in the field of view. To distinguish a faint, distant galaxy from this sea of closer stars requires exceptional resolution and observations across multiple wavelengths. Some areas are simply so crowded that confusion becomes the dominant factor, making detection nearly impossible. Observing in infrared light helps to mitigate this issue, but it cannot resolve the problem entirely. Stars also emit infrared light, especially the red giant stars that are common in the galactic bulge. A faint, faraway galaxy might look very similar in brightness and color to a foreground red giant. Separating the stars from the galaxies requires a detailed analysis of each object's properties, a process that begins to fail when too many sources are clustered together. Radio observations are better at avoiding this stellar confusion, as most stars produce very little radio emission. However, these observations are susceptible to contamination from other radio sources. The remnants of supernovae, pulsars, and vast regions of ionized gas all generate radio waves that can easily mask the faint signals from distant galaxies. The galactic center is particularly rich with these kinds of sources, creating a noisy and complex radio background. It is conceivable that some regions might be hiding structures that are larger and more distant than anything we have yet discovered. If a massive supercluster of galaxies were situated directly behind the galactic center, it could remain undetected indefinitely. The extreme obscuration would block its optical and infrared light, while its radio signals might be mistaken for emissions from local sources within our own galaxy. Only indirect methods, such as searching for gravitational lensing effects or mapping cosmic velocity fields, might one day reveal the presence of such hidden giants. There are also certain areas that suffer from incomplete survey coverage. A majority of the world's major astronomical facilities are located in the northern hemisphere, which naturally leads to better coverage of the northern sky. The zone of avoidance stretches across both hemispheres, but some of its southern portions have received comparatively less observational attention. These undersurveyed regions could very well contain significant cosmic structures waiting to be discovered once comprehensive surveys are finally conducted. A modern challenge for ground-based observations comes from the proliferation of satellite constellations. Thousands of communication satellites are being launched into low Earth orbit by various companies. These satellites reflect sunlight and broadcast radio signals, which appear as bright streaks in astronomical images and create interference for radio telescopes. As these constellations continue to grow, the task of observing faint objects through the zone of avoidance from the ground becomes progressively more difficult. Observatories in space are immune to satellite interference, but they face their own set of limitations. Both Webb and Roman operate at infrared wavelengths, where the telescope's own heat can generate a background noise that contaminates the data. Sophisticated cooling systems are used to mitigate this effect, but they cannot eliminate it completely. At the longest infrared wavelengths, this thermal background becomes the limiting factor for sensitivity, making it harder to detect faint, distant sources through heavy dust. Future technologies may offer solutions to some of these persistent limitations. The technique of interferometry, which combines light from multiple telescopes spread over large distances, can achieve a resolution that is impossible for any single instrument. Radio interferometers have already demonstrated this remarkable capability for years. In the future, infrared interferometers deployed in space could potentially resolve individual galaxies within extremely crowded fields, pushing past the confusion limits that constrain current telescopes. Advanced image processing techniques and machine learning algorithms are also proving invaluable for extracting faint signals from noisy data. These computational tools can identify faint galaxies hidden among bright foreground stars or help distinguish real astronomical sources from instrumental artifacts. As these algorithms continue to improve, they may uncover objects in existing datasets that were previously missed by human analysis. Yet, despite all this progress, a degree of uncertainty about the very deepest regions of the zone of avoidance is likely to persist. It may never be possible for scientists to create a truly complete catalogue of every single galaxy in the most heavily obscured parts of our sky. The universe, it seems, does not reveal all of its secrets to direct observation, meaning that indirect methods must continue to fill in the missing details. Still, a complete understanding of everything concealed behind the Milky Way's galactic plane might forever lie just beyond our grasp. The profound question is what this means for our perception of cosmic structure. Discovering enormous structures within the zone of avoidance fundamentally reshaped how astronomers perceived the universe's large-scale organization. With 20% of the sky effectively missing, we were also missing essential components of the cosmic web, which introduced distortions into our picture of how matter is distributed throughout space. From the very first surveys of galactic distribution, an obvious structure was apparent. Galaxies tend to congregate in groups, and these clusters subsequently align themselves along immense filaments. In contrast, vast voids contain very few galaxies. This intricate pattern, which came to be known as the cosmic web, was revealed by mapping millions of galaxies across the heavens. The resulting maps, however, featured a massive hole where the zone of avoidance obstructed the view. This observational gap posed significant challenges. The situation was akin to trying to comprehend an elaborate spiderweb while being able to see only 80% of its threads. While the general pattern might be discernible, many of the crucial connections would remain hidden. In a similar way, the large-scale structures that traversed the zone of avoidance appeared disconnected in astronomical surveys. Scientists could identify portions of these structures emerging on either side of the obscured band, but they lacked the ability to confirm if these segments were actually linked. It was the discovery of the Vela supercluster that finally resolved some of these connections. This immense structure effectively bridges a major gap within the cosmic web, linking together concentrations of galaxies and constellations on opposite sides of the galactic plane. The confirmation of this link provides strong evidence that the cosmic web continues uninterrupted through regions we cannot easily see, maintaining the same filament-like pattern observed elsewhere. For cosmology, understanding the completeness of this structure is of paramount importance. Researchers use the distribution of galaxies to rigorously test theories about the universe's composition, its history of expansion, and its most fundamental properties. If these surveys fail to account for major structures, the conclusions drawn from them become biased. The zone of avoidance introduced just such a systematic bias, one that could potentially skew our understanding of how matter aggregates. As an example, any attempt to measure the universe's overall matter density depends on counting galaxies across representative volumes of space. Overlooking 20% of the sky could lead to a miscount of galaxies by a similar margin. In practice, the bias is far more complex, as the level of obscuration varies across different parts of the zone of avoidance. Making accurate corrections requires sophisticated modeling to estimate how much structure is likely concealed in these unmapped regions. The discovery of unexpectedly massive structures within the zone of avoidance prompted concerns about what else might be hidden there. The fact that the Vela supercluster remained undetected until 2016 raises the question of whether other structures of comparable mass could still be awaiting discovery. Each new detection alters our estimates of how matter is distributed, which in turn affects a wide range of cosmological calculations. The discovery of the Great Attractor was a clear demonstration of how a hidden structure could influence galaxies we can observe. Our own galaxy's motion toward this obscured region was once a mystery, until observations uncovered the concentration of mass responsible for it. It is plausible that other peculiar galactic motions could be the result of hidden structures that have not yet been found. Mapping the zone of avoidance is therefore essential for explaining these movements. The information gathered from surveys of the zone of avoidance is now being integrated into large-scale structure models. Simulations that model the evolution of the cosmos can then compare their predictions against these more complete observations. This provides a better test for determining whether models of dark matter and dark energy are accurately describing reality, especially when they must account for newly found galaxies and clusters in formerly obscured areas. This process either strengthens or challenges various theoretical frameworks. Certain theories, for instance, predict specific differences in how cosmic structure should appear at different scales. Comparing observations across multiple scales allows these predictions to be tested. The zone of avoidance offers crucial data at intermediate scales, bridging the gap between local galaxy groups and the very largest superclusters. Filling in this missing information enables more rigorous testing of theories on structure formation. These discoveries also have a significant impact on our understanding of how superclusters form and evolve over time. Current models predict that structures grow hierarchically, with smaller objects forming first and then merging to create progressively larger systems. By observing superclusters at various distances, we can see this evolutionary process in action. The Vela supercluster and the Great Attractor serve as nearby examples that can be studied in great detail. Measuring the flow of galaxies toward attractors like the Shapley supercluster also reveals information about dark energy. This enigmatic force is responsible for accelerating the expansion of the universe, working in opposition to gravity. The delicate balance between gravitational attraction and this accelerating expansion ultimately determines whether structures will continue to grow or will be frozen at their current sizes. Measurements of galactic velocities help constrain the strength and behavior of dark energy over cosmic time. Studies of the zone of avoidance make a direct contribution to these measurements. Every new data point on velocity helps to map these cosmic flows with greater accuracy. The region of the Great Attractor is especially valuable in this regard, as many nearby galaxies exhibit motion that is influenced by the structures located there. To untangle the individual contributions from various mass concentrations, it is essential to know what actually exists within these obscured regions. Future cosmological surveys will routinely incorporate data from the zone of avoidance. There are upcoming projects designed to map billions of galaxies across the entire sky, including the obscured regions, by using infrared and radio observations. These comprehensive surveys will at last remove the systematic gap that has complicated cosmology for more than a century. A compelling question remains: could even more massive structures still be hiding in this cosmic blind spot? The discovery of the Vela supercluster naturally raised this possibility. If such a massive structure could remain hidden until so recently, it stands to reason that others might still be waiting to be found. The zone of avoidance conceals roughly 20% of the extragalactic sky. Statistically, it should therefore contain about 20% of all massive structures at any given distance. Most superclusters at a distance comparable to Vela would have likely been detected by now if they were located in a clear part of the sky. The Shapley supercluster, although more distant, was discovered decades ago simply because it does not lie within the zone of avoidance. Vela remained hidden only due to its unfortunate position directly behind the galactic plane. This suggests that very few comparably massive structures at similar distances remain completely unknown. However, the laws of probability do allow for surprising outliers. It is possible that random chance has concentrated several massive structures within these obscured regions. And what is certain is that current surveys have detected only a fraction of the total number of galaxies hiding in the zone of avoidance. Charting the entire cosmos is an endeavor that requires many years of telescope time, which means some regions of space are still only sparsely studied. Because of this, the possibility of making additional major discoveries seems quite plausible. Scientists have, in fact, pinpointed several potentially massive structures based on indirect forms of evidence. The peculiar velocities observed in some galaxies, for example, suggest the presence of matter concentrations in obscured areas beyond those we have already confirmed. Some of these velocity patterns could be hinting at undiscovered superclusters with a scale comparable to Vela. Other patterns might simply represent smaller structures, or perhaps just statistical fluctuations within the broader distribution of galaxies. One candidate region of interest is located in the constellation Puppis. Velocity measurements there show galaxies moving in ways that are consistent with a massive, unseen attractor lying beyond the zone of avoidance. While preliminary radio and infrared observations have detected concentrations of galaxies, a complete map of the area awaits more extensive surveys. The structure itself might ultimately rival the Vela supercluster in mass, or it could prove to be something on a smaller scale. Another potentially significant formation appears to be situated in the northern zone of avoidance. Counts of galaxies near the edges of this obscured region suggest that known structures continue across it. The central portions, however, remain inadequately sampled. It is impossible to determine whether this represents a new supercluster or merely the expected extension of known formations without better observations. Detecting more distant structures is even harder, even when looking through a clear patch of sky. Superclusters that are more than 1 billion light-years away appear faint and small simply because of their distance. Placing such a structure within the zone of avoidance makes it nearly impossible to find with our current level of technology. It is conceivable that several such formations exist, still undetected, waiting for future surveys equipped with far greater sensitivity. The probability of making major new discoveries does diminish as our surveys become more thorough. Every new galaxy that is detected helps to constrain the possible structures that could exist in unmapped regions. If current surveys have now located most of the galaxies brighter than a certain limit within these obscured areas, then any undiscovered structures that remain must consist primarily of fainter galaxies. This, in turn, places a limit on their total mass and their gravitational influence. Computer simulations can offer valuable guidance on what we might expect to find. Researchers are able to run simulations that match the universe we observe, incorporating the same distribution of matter and the same history of expansion. These simulations generate mock universes that are statistically similar to our own reality. By studying what kinds of structures form in the simulated zones of avoidance, scientists can estimate what is likely hiding in our real one. These simulations suggest that a few more structures on the scale of a supercluster probably do remain undetected. The precise number depends on the specific details of how cosmic structures form and just how effectively interstellar dust blocks our view. Most estimates place the number of undiscovered structures comparable to Vela at somewhere between 2 and 5. It is also likely that dozens or even hundreds of smaller structures still await detection. The possibility of making completely unexpected discoveries, of course, always remains. Every major astronomical survey seems to reveal surprises that existing theories had not predicted. The zone of avoidance might just contain anomalies or unusual structures that are unlike anything seen in the better surveyed parts of the sky. A low probability does not mean something is impossible. Some researchers have even speculated about truly enormous structures that could be hiding behind the galactic center. A hypothetical supercluster, larger than anything currently known, could theoretically exist directly behind the thickest part of the obscuration. The evidence for such a formation remains weak, based mostly on small anomalies found in galaxy velocity patterns. While most astronomers consider this scenario unlikely, ongoing observations continue to test the possibility. The ultimate question is whether any of these undiscovered structures would truly matter for cosmology and for our understanding of cosmic motion. If they exist but contain masses comparable to known structures, their discovery would certainly be interesting, but it would not be revolutionary. Only finding something truly unexpected, or something much more massive than predicted, would fundamentally change our picture of the universe. The current evidence suggests that the major mass concentrations influencing our cosmic neighborhood have now been identified. The Great Attractor, the Vela supercluster, and the Shapley supercluster can account for most of the peculiar motions we observe. Any additional discoveries would likely refine our understanding, but probably not overturn it. The universe probably holds fewer dramatic surprises in the zone of avoidance than it did just a decade ago. Nevertheless, the work of creating a comprehensive map continues. The revelations that have come from studying the zone of avoidance have already transformed how scientists understand motion through the universe. What once seemed like mysterious, unexplained velocities now fits into a coherent picture of gravitational attraction playing out across multiple scales. Our own trajectory through space finally makes sense when we can see the complete landscape of mass distribution that surrounds us. Before the discovery of the Great Attractor and the understanding of its relationship to even larger structures, astronomers struggled to explain why our galaxy was moving in its particular direction. Standard cosmology predicted that galaxies should simply ride along with the expansion of the cosmos, moving away from each other smoothly. The existence of large, peculiar velocities suggested something was wrong with either the observations or the theory. The discovery that massive structures were hiding in the zone of avoidance resolved this tension. Our peculiar motion is the result of gravitational attraction toward these structures, exactly as the laws of physics predict. There is nothing mysterious or anomalous about it. We are simply falling toward concentrations of mass, much like water flowing downhill, following the contours of the gravitational landscape. Understanding the causes of our motion allows us to make predictions about our future path. Over the next billion years, our local group of galaxies will continue its drift toward the region of the Great Attractor. However, because of the accelerating expansion of the cosmos, we will never actually arrive. The distance between us and the attracting structures will eventually begin to increase, as cosmic expansion overpowers their gravitational pull. Our trajectory will curve, asymptotically approaching a maximum displacement before recession ultimately takes over. This future plays out differently for structures at different distances. The local group and the Andromeda Galaxy will merge in roughly 4 billion years. Their mutual gravity is strong enough to overpower local expansion. This newly merged galaxy might then interact with other members of the local group, eventually creating a single, giant, elliptical galaxy. This process will happen regardless of any external attractors. The Great Attractor itself will continue to pull surrounding structures together. Galaxy clusters within a few 100 million light-years will gradually fall into that region, merging with the clusters that are already there. Over a timescale of tens of billions of years, this gravitational gathering could forge an immense galaxy cluster, one of the most massive bound structures known in the universe. The influence of dark energy, however, will prevent anything more distant from ever joining this cosmic merger. A similar fate awaits the Shapley supercluster, which will continue to collect matter from its local environment even as cosmic expansion isolates it from faraway structures. Ultimately, the Great Attractor region and Shapley will each evolve into isolated superclusters, adrift in an ocean of ever-expanding voids that carry all other structures away from them. On even grander timelines, stretching tens or even hundreds of billions of years into the future, it is possible that dark energy could dismantle these gravitationally bound systems. Current observations are not yet able to resolve whether the strength of dark energy increases over time. Should it intensify, its repulsive force could eventually overwhelm gravity on every scale, tearing apart galaxies and even solar systems in a theoretical end state known as the Big Rip. A deeper understanding of present-day cosmic motion is crucial for constraining the properties of dark energy and forecasting these potential futures. The delicate equilibrium between gravitational attraction and cosmic expansion is critically dependent on the strength and behavior of dark energy. By measuring the actual speed at which structures move toward attractors, scientists can test whether dark energy aligns with theoretical predictions. Some earlier measurements, in fact, revealed anomalies that prompted considerable debate. The motion of our own local group appeared to be slightly faster than models predicted, based on the visible distribution of matter. This discrepancy pointed to either undiscovered mass hidden within the zone of avoidance or potential flaws in our models of dark energy. The discovery of the Vela supercluster helped to resolve a significant part of this puzzle by accounting for a large amount of previously unknown mass. Any small, remaining variances in motion might suggest the presence of other hidden structures, or perhaps subtle deviations in the nature of dark energy itself. The data also provides a rigorous test for our understanding of gravity. Einstein's theory of general relativity precisely predicts how mass warps spacetime to generate gravitational attraction, and alternative theories of gravity offer slightly different forecasts. Measuring the motions of galaxies with sufficient accuracy allows astronomers to verify whether general relativity holds true at the vast scales of superclusters. To date, observations have aligned with the predictions of general relativity with remarkable fidelity. The movements of galaxies toward the Great Attractor, Shapley, and other massive structures conform to the patterns anticipated by Einstein's theory. This consistency validates the use of general relativity in cosmological calculations and in models that simulate the formation of large-scale structure. Our comprehensive view of cosmic motion has emerged from a synthesis of observations across many different wavelengths and distance scales. While optical surveys meticulously mapped galaxies in unobscured regions of the sky, infrared and radio observations work to unveil the structures concealed from view. Measurements of velocity revealed the intricate patterns of movement, and sophisticated simulations integrated all of this information into a coherent framework that explains what we see. This remarkable achievement stands as a testament to the power of persistent scientific inquiry. The mystery of our peculiar motion required decades of work to unravel, depending on technological breakthroughs and comprehensive surveys of the entire celestial sphere. Although the zone of avoidance posed a formidable challenge, astronomers devised innovative methods to peer through the veil. The result is a profound understanding of our own position within the cosmic web and the specific path we travel through it. The question then becomes, what else remains to be discovered in these hidden realms? The next decade is poised to bring about revolutionary progress in mapping the zone of avoidance. Several missions are currently in development that will extend our observational reach far beyond the limits of today's telescopes. The combined power of these new instruments should finally allow us to see nearly everything that lies hidden behind the plane of our galaxy. The Nancy Grace Roman Space Telescope, slated for launch in the late 2020s, is set to perform the largest infrared survey ever conceived. Its wide-field camera can observe an area of the sky 100 times larger than the instruments on Webb, all while retaining exceptional sensitivity. Throughout its mission, Roman will image thousands of square degrees across the zone of avoidance, cataloguing hundreds of millions of galaxies. Furthermore, Roman's spectroscopic abilities will enable it to measure the distances and velocities of these galaxies. This mission is expected to generate three-dimensional maps of the obscured universe with an unprecedented level of detail. Structures like the Vela supercluster will be rendered in their entirety, revealing every significant galaxy and cluster across their full expanse. Meanwhile, the Square Kilometre Array, a next-generation radio telescope being built in South Africa and Australia, will completely transform surveys of hydrogen emission. This facility will link thousands of individual antennas spread over vast distances, yielding a sensitivity that far surpasses that of Meerkat. In regions where Meerkat detected hundreds of galaxies, the Square Kilometre Array may well detect tens of thousands. This dramatic increase in sensitivity will make it possible to detect neutral hydrogen at much greater distances. While current surveys can effectively probe out to a distance of about 1 billion light-years, the Square Kilometre Array will extend this reach to several billion light-years. This will allow it to map cosmic structures through the zone of avoidance across a substantial portion of the observable universe. Ground-based extremely large telescopes, which are set to begin operations in this decade, will also provide crucial observations. The Giant Magellan Telescope, the 30-meter telescope, and the Extremely Large Telescope all boast primary mirrors that are far larger than any existing instruments. Paired with adaptive optics to cancel out atmospheric distortion, they will achieve a resolution comparable to space telescopes, but with a vastly superior light-gathering capacity. These observatories will be able to study individual galaxies within obscured clusters measuring their physical properties and stellar populations. This research will help test theories of galaxy formation by determining if galaxies in the zone of avoidance are different from those in more thoroughly studied regions, as heavy obscuration might introduce observational biases that current studies have overlooked. Advanced survey strategies will also be employed to maximize the efficiency of these new tools. Rather than observing random patches of sky, future surveys will focus on areas where models predict the existence of significant undiscovered structures. Machine learning algorithms will analyze incoming data in real time, flagging interesting targets for immediate and more detailed follow-up observations. This targeted methodology is expected to accelerate the discovery of any remaining massive structures. The spirit of international collaboration is also growing, leading to more coordinated observations. Projects such as the Legacy Survey of Space and Time at the Vera C. Rubin Observatory will produce enormous datasets that will be accessible to scientists all over the world. Combining information from multiple facilities creates a much richer and more complete picture than any single telescope could achieve on its own. The study of the zone of avoidance is a particular beneficiary of this collaborative approach, as different instruments possess unique strengths at different wavelengths and with different observational techniques. Astronomers anticipate that within the next 15 years or so, they will have identified nearly every galaxy above a certain brightness across the entire zone of avoidance. The resulting catalogues are expected to hold information on tens of millions of galaxies, detailing their positions, distances, velocities, and fundamental characteristics. This achievement will finally close the persistent gap in our maps of the universe. Such a comprehensive survey allows for the study of how cosmic structures evolve over time. By comparing formations that are close to us with those seen far away, researchers can watch the story of how galaxies clustered and combined over billions of years. The zone of avoidance offers essential lines of sight for this work, uncovering structures at distances that enrich observations made in other parts of the sky. The wealth of data will put cosmological theories to the test with an unprecedented level of precision. Current models make specific predictions about the patterns of structure formation, the history of cosmic expansion, and the distribution of dark matter. When these predictions are compared against such thorough observations, the models are either confirmed or discrepancies emerge that point toward the need for new physics. Every single galaxy that is newly detected becomes another piece of evidence in this grand evaluation. Even with these remarkable advances, some questions will likely remain unanswered. The most densely packed regions near the galactic center may stay at least partially hidden, even from the most advanced future instruments. Certain types of measurements, which depend on resolving individual stars within faraway galaxies, will remain impossible through the thickest curtains of dust. Gaining insight into the earliest formation history of these obscured structures might require observational capabilities that physics itself does not permit. Nonetheless, the journey from a state of near-total ignorance to one of comprehensive knowledge is an extraordinary accomplishment. A century ago, astronomers were not even aware that other galaxies existed as distinct islands beyond our own. Just 50 years ago, the zone of avoidance was considered a permanently impenetrable veil. Today, we are actively detecting the immense structures concealed there. Soon, we will have charted them completely. The hidden cosmos gradually surrenders its secrets. Each technological leap peels away another layer of obscuring material. What is invisible to us now may become visible in the future. The Great Attractor, once a profound mystery, is now understood as just one piece of a cosmic web we can trace for hundreds of millions of light years. The Vela supercluster materialized from obscurity to claim its place as one of the largest known structures in our cosmic neighborhood. Discoveries like these are a potent reminder of how much remains unknown, despite everything we have learned. The universe holds mysteries we have not yet begun to imagine, hiding in plain view behind obstacles we have not yet surmounted. For more than a century, the zone of avoidance was one such barrier. New obstacles surely await, challenging future generations to invent new tools and methods for perceiving what now seems invisible. The voyage from ignorance to understanding is a journey without an end. Each answer simply uncovers a new set of questions. Every discovery opens up new realms of possibility. The colossal structures that were hiding in our galaxy's blind spot teach us a valuable lesson in humility about our current knowledge. while also inspiring excitement for what is still left to be found. The cosmos reveals itself to those who are persistent enough to keep looking. Even when a curtain of dust and stars blocked the view, we continued our search. We discovered giants lurking in the darkness. And we will persist in our observations until every secret yields to the power of human curiosity and ingenuity.